Hey guys, welcome back. So today we're going to focus in on residuals. So let's kind of review a few things. We're still talking about the Burger King menu. I think I posted on top of the assignment again today just so you can see that data. You've also got your summary statistics over here. So for the protein, that's our explanatory variable. Our response variable is the fat content. We have the X bar and Y bar, which are the averages, and then the standard deviations for those different variables, and then the correlation between the two. Remember, that's calculated by finding the sum of the z-score, the products of the z-scores divided by n minus 1, which was 30 in this case. And then from that we got the model. So the model is going to be this red line here. Now remember, the model will always go through the mean point, which is when we have an average protein content, we would expect to have an average fat content as well. So that's going to be this point here, 17.2 and 23.5. Okay. Now finding the slope of the line of best fit, or the regression line, is going to be found by taking the sum of the products of the z-scores. Remember that. Okay, so the sum of the products of z-score, that's where we get the correlation coefficient divided by n minus 1, right? And then we multiply that by the standard deviation of fat divided by the standard deviation of protein, which will take it back to the real world units and allow us to get this value right here, this 0.972 times x. Okay, then this is our y-intercept, in other words. Okay. All right. So remember, whenever we create a model, so in this color here, that's the actual model itself, right? The model is just a representation, a helpful representation of the data itself. Okay, so we use the data to create the model, and then once we have the model, we don't really need the data anymore. We just use the model to make predictions, right? So we can predict the actual fat content based on the whatever protein content you tell me. Okay, now there are some important things that we can get from the residuals, and we're going to talk about that for a little bit. So the residuals is also written as an E. So remember, we have RAP, residual is equal to the actual minus the predicted. Well, the actual data is going to be the Y values. The Y hats are the predictions, which are going to be the values that are going to be the X values evaluated for the Y1. I can actually show you that here. So let me put in here, so stat edit. So in list 1 here, that's going to be all of my protein values. List 2 is going to be the actual model, it's going to be the actual fat content as well. And so if I want to find the residuals, what I can do, so I'm actually going to clear this out real quick, and I'll show you how you can calculate residuals. Now, the easy way to calculate residuals, I guess I'll show you that real quick, is just to go to stat, arrow over to calculate the fourth one. We're going to go from line 1 to line 2. We're going to store the regression equation in variables, y variables, function y1, and then hit calculate. Okay, so anytime we calculate a linear regression, it's going to it will actually give you, if you go to the list option, so second stat list option, the residuals are going to be here. So that's going to be the list of the residuals. Now, if you want to, you can actually go into stat and then edit. And for list 3, you can hit enter, and then you can define list 3 by the residuals. Okay, so that's the easy way to get the residuals. Now, another way that you can get the residuals, remember, the residuals is the actual minus the predicted. So the actual data that we're looking for are the Y values from the fat content. So that's going to be list 2, so second 2, minus the predicted. Now, to get the predicted, we're going to take the X values here, and we're going to evaluate them into our model to get the prediction. So wherever those are going to line up on the model. So I'm going to go to second, or sorry, not second, just variables. Okay, yeah, so variables, y variables, function y1, and then I'm going to evaluate that at list 1, which is going to be our x values. So the function evaluated at the x values, our domain, is going to give us the set of predictions, and we're going to take the set of the actual values minus the set of their predictions, and it's going to line those up. So the first one, the second one, the third one, the fourth one, and go all the way through, and that's what's going to give us that. Now, if we look at that, doesn't that look exactly the same as the residuals? What do you know? So you'll never need to know how to do that. You'll just use it. The calculator does it for you, okay? But I just want to show that to you. So now that we have this list of the residuals, which is either list 3 or list 4, it doesn't really matter anymore, we can evaluate those pretty good. So some of the residuals are positive, meaning that the actual data was had more fat content than we expected, and then some of them are going to be less negative residuals, just meant that the actual was less than we predicted, or less than we expected from the model. Okay. Also keep in mind the model is not going to fit the data exactly, just like a bell curve. A normal model doesn't fit the actual histogram exactly. It's just useful, and that's why we use it. All right, so we always graph the residuals. I will show you how we can do that here. So I'm going to graph list 3 or list 4 because they're exactly the same. So second y equals stat plot. We usually graph the residuals about the x-axis. Sometimes they actually graph it about the predictions, which is quite interesting. But we're just going to use the x-axis because it makes more sense. And then I'm going to graph that about list 3. Again, list 3 and list 4 were the same, so it wouldn't matter how we've done it. And then zoom 9. There you go. Okay, so I've got some models showing up here. Luckily, I'm not getting the wheel of death. So if I go to y equals, I can turn those models off by arrowing over the equal sign and then hitting enter. So they're still stored there. They're going to be turned off so that they're not bugging us. All right, and then this line here, this 0 line, that's the actual model itself. So instead of being a diagonal line, it's now going to be horizontal. Okay, so that's our model, sorry. And then they're going to have the positive residuals on the top and the negative ones on the bottom. Okay, no big deal. So when we're looking at residual plots, we're looking for no pattern. If there's no pattern, that means that it's linear and we're good to go. You also could have a fan pattern. You need to make sure that you have equal spread about here. I'll show you that on another slide as well. Make sure there's no outliers, crazy outliers that might be messing up the model. And I think that's it. Yeah, so make sure there's no curvature, no outliers, no fan, and it needs to be random, and it is. Now, once we have this data here, what we can do is we can actually find the standard deviation of the residuals. So the residuals is kind of like the error that we have in the plot, and that's why we actually use the E right here, this E, it stands for error. So what error do we have? So all these pieces here are how far off the model was from the actual data, which would be the error in the model, which is kind of cool. So we can actually find the standard deviation of the error by taking the sum of this is basically this is the actual minus the predicted, so or how far it is from the mean. Anyway, basically we're finding standard deviation. Okay, so we're finding standard deviation for, I think this came from something else. This is the actual standard deviation, but it's slightly different because we're basically evaluating not from the average, but evaluating it from the model itself. So it would be the actuals minus the predicted squared, the sum of those, and we divide by the n minus 1. Okay, so with that thought in mind, let's take a look at this again. So here I've graphed out the histogram of just the fat content. So it's on its side, but you know, we can do vertical histograms, which is totally fine. And then here's the average in the blue line here. Now, if we didn't use the model, if we didn't use protein to be able to make predictions about the fat content, we would be stuck with just a model that was a horizontal line that's just going to be the average fat content. And that's what we would guess regardless of what the protein was. But now that we know there's an association, that allows us to change the slope, and notice they're still going through the mean point. Kind of clever, right? So now allows us to change the slope to follow the association. So the further that we get away from the mean of the protein, the further we can get away from the mean of the fat content as well, by using the correlation coefficient as kind of like our scale factor, in other words, okay? Which that allows us to have that much confidence to be able to deviate that many standard deviations from the mean. So anyway, over here I wrote the total amount of variation that we have in the fat content. Now that's found by taking the standard deviation of the fat content and squaring it. If you remember, the variation is going to be the standard deviation squared, okay? So 16.4 squared with more precision. And in fact, I can show you how I did that. So anytime we run a linear regression, which I'm going to go ahead and run one again, because it's pretty easy to do, it will, no, I don't run a linear regression, I'm sorry. I need to run two variable stats. Okay, so when I run two variable stats, list 1, list 2, that's going to give me the mean and standard deviation and all this stuff. Now, if I want to find the actual standard deviation of y, okay, so the s sub y, this value here, and I want to square it because I want to use all the precision, what I would do is I would go to variables, the fifth option, which is stats, and then go down to s sub y, which is the sixth option, and then I can take that value and square it. And now if I just hit enter, that's that value, which is kind of cool. So what I'm going to do is I'm going to take the value and I'm going to square it, And this is what's going to allow me to have all the possible precision. And that's where I got this number here. So anyway, cool stuff. Really nice. I'll show you that again. So variables, arrow down to the fifth option, which is statistics. And then here's all the variables that came from running two variable stats. We also, if we look down here, we'll also have the correlation coefficient, which comes from the equation. So EQ is the equation. So if you want to know the correlation coefficient, you can do that. You might have to recently run it before it'll let you do that. So I'll show you that real quick. So if I do stats, hit calculate, linear regression, run the linear regression. Okay, so that's good. Now what I'm going to do is go back and rerun the R, and now it'll work. So it only works for whatever you most recently ran. Okay, so that's kind of the downside. But anyway, really good stuff there. I guess I'll show that to you again. Of course, you should probably be looking at this on your own calculator. But just in case you weren't following along just because, you know, work. We went to the equations, and we have the correlation coefficient, which is R. We also have the R squared, which is going to be the coefficient of determination, and which is just going to be when we square the R value. And then the other one we had is the R squared, which it didn't like giving that to us. Huh. Well, anyway, the capital R squared and the lowercase r squared, I believe those are exactly the same thing. Maybe in the calculator they're using the capital R squared for something else. But that's okay. All right, so anyway, let's get back to this. Sorry for the diversion here. So here I've grafted the standard deviation, kind of the box plot for the error. Okay, so this is like if I went up and down the model and I collapsed all these residuals here, that's what this box plot is showing here. Okay, so to the maximum, to the minimum, the quartiles, and all that good stuff. And it's centered about the mean, which is going to be, sorry, not the mean, the model itself. Okay, so this has, if I took the amount of error that we had and I evaluated the standard deviation. So what I'm going to do to find the standard deviation, the error, remember our error was the third list 3. Okay, so what I'm going to do is I'm going to go to stats, not stats edit, sorry, stats, calculate one variable stats, and I'm going to do list 3 or list 4, remember they were the same thing. And this is going to give me the standard deviation of 9.12. And now I want to actually square that to get the variation. So I'm going to go to variables 5. I'm going to do standard deviation of x because it was the x term in this case because I only ran one variable, which is that value, of course, in case you were, you wanted to double check and make sure that it was right. And I'm going to square that to get the variation, and boom, that's where I got this number with all the precision. Okay. All right, so we have this much variation in the fat content initially. Okay, that's the total amount of variation we have in fat content. The model was able to remove a lot of the variation, but this is the amount of variation that remains. That came from the standard error, not standard error, but the standard deviation of the error. Those are two slightly different things. Anyway, and so if we subtracted these two, how much of the variation did the model actually remove? So if I subtract this from this value, that means that this was how much variation the model was able to remove, and that amount percent of the total is going to be 69%, which is our R squared, which the R squared is the same thing as squaring the correlation coefficient. So that's a huge concept and should blow your mind. So let me slow down again. Okay. Whenever we get our correlation coefficient and we square it, so 0.83 times 0.83 would give us 0.69. Okay, that's this R squared, and it's shown with a capital R, but it really is just the correlation squared, so don't worry about that. Okay, that is the coefficient of determination, which tells you the amount of variation in the model, or sorry, the amount of variation in the response variable, like the fat in this case, that is being accounted for or removed by using the model. So instead of having all this variation in our estimates by just having the horizontal, just guessing the mean every time, by using the model, we were able to remove a lot of the variation, and 69% of the total variation overall, which is really, really fascinating. And the remaining 31% of the variation is going to be the variation that's still remaining, left unaccounted for by the model, and that's going to be the variation that is shown and seen in the error or in the residuals. Kind of cool. All right, so if we have the correlation coefficient 0.83, R squared is the variation accounted for by the model, also known as the coefficient of determination, which is just it's a totally cool name, right? Coefficient of determination. Anyway, so that's how much of the variation was removed by about 69%, which is the same thing as squaring the r, by the way, kind of cool. So if we do 1 minus the r squared, if the r squared is how much variation is removed, 1 minus the r squared is going to be how much variation is still left remaining in the residuals, which was this value from the residuals divided by total, which is 31%, and that's the exact same thing. So I'm just kind of reiterating it. All right, so a few questions and we're pretty much done. So I'm trying to make the videos a little shorter for you, but this is really good, really, really good content. By the way, this unit I think is by far my favorite because there's just so many cool like meta math concepts going on, and the calculator is like so stinking cool, and there's just so many tricks I get to show you guys. And honestly, all the things that you can do in the calculator with statistics and the variables and all the fun stuff, like it is really, really impressive. I had no idea I would enjoy this so much, and this is probably one of my favorite units. Definitely. All right, so I'd probably say that about every unit anyway. All right, so what is the standard deviation for the y variable, or the standard deviation for the fat content of the 32? There's actually 31 Burger King menu items. So that was found from our summary statistics. We already knew that. What's the variation in fat content for those items? So the variation is found by squaring the standard deviation. So that's how we got that value. What is the standard error, or sorry, the standard deviation of the error, or the residuals? We use an E for error instead of using R for residuals, because R is used for the correlation coefficient. So that's why they kind of use it for error. For the residuals of our linear model. So that was found by taking the residuals, defining that as a plot, as a list, and then running one variable stats on it. Okay. What's the variation in residuals? We square it, no big deal. What's the variation in the fat content left unaccounted for by the model? So we take, oh, that's the same question. Yeah, so that's the variation of the residuals is the amount of fat content left unaccounted for by the model. What's the variation in the fat content that's accounted for by the model? Well, we would take the total amount of variation in fat minus what was still left unaccounted for, and that would tell us how much variation was successfully removed by using our model, which is nice. All right, so what proportion of the variation in fat content is accounted for by the model? That's how we define an R squared, by the way. That should sound really familiar. So this is how much was removed divided by the total amount of variation, which is 69%, which is the same thing as squaring the correlation, which is really, really, really groovy. All right, moving on, number 7. So hey, not too bad, under 18 minutes. All right, the correlation between cereal's fiber and potassium contents is R is equal to that value. That's the correlation. All right, what fraction or percent of the variability in potassium is accounted for by the amount of fiber that's the servings contain? So if we want to know, this is the coefficient of determination. So the amount of proportion, we would just take the correlation and square it, which would give us 0.815. So 81.5% of the variation in potassium is accounted for by the model with fiber. Kind of cool. All right, residuals. Tell what each of the residual plots indicates about the appropriateness of the linear model. So all these are residual plots. You see the 0 here, that's the model. They just didn't draw the line on them, okay? So the first one, this is totally random. There's an even amount of spread vertically. As we go look across here, it's all the same. So this should tell us that it's appropriate. So this is what we're looking for. Okay, we're looking for randomness and equal spread and no outliers. Okay. Now on this one we have curvature, which means that we were trying to fit a square peg in a round hole. I'm just kidding. No, but kind of similar. We're trying to fit a curved data, curved association with a linear model, which is not appropriate. So what we need to do is re-express the data first, then it will get a randomized pattern, and then we're all Gucci. Yes, I said that. And then the other one is a fan. This is called fan behavior. So fan behavior is not like a total issue, but you do want to make sure that you tell people about it. So all this means is that with smaller x values, the model's more accurate. But as we get towards the larger x values, kind of almost like extrapolating, but not quite, as we get further out away from the mean in the positive direction, the consistency or the variation is going to be much higher. Okay, so there's going to be more spread. So our model kind of breaks down as we get further higher towards the higher values. So that's the problem with the fan. Okay, so you can still use the model. There's no way to fix this, like re-expressing curve data. There's no way to fix this. It's just you want to state that that's what's going on whenever you do it. Okay, so that's what those tell us about. So again, this one's kind of like, it's kind of an issue, but you just want to talk about it, tell people what's going on, so they don't think they have as much confidence all across the board for the x values. All right, so graph of the residuals. So if we have a curve pattern, that's not good. We need to re-express it. We want equal vertical spread. So this is fan behavior going the other direction. And then make sure you don't have any outliers, which that was not given in the example. So I want to point that out, because an outlier will mess up, it'll mess up your line. It'll also increase the standard deviation more than we should. So a lot of times when we do actually have outliers, we can remove them, and that as long as we tell people that's what we're doing. We just want to find a model that fits the typical data the best, and if the outlier messes it up, then hey, just remove it. Just make sure you're being honest about what practices you did, so people don't accuse you of like cherry picking data. Okay. All right, cigarettes. Is the nicotine content of cigarettes related to TARS? Wow, this is like Tarzan. A collection of data in milligrams on 29 cigarettes produced the scatter plot, residuals plot, and regression analysis shown. So this whole regression analysis, this is why I want to do the problem with you. This is a regression analysis right here. So they're telling us the dependent variable is nicotine. So the dependent variable is going to be, that's going to be what we are, it's going to be our response variable. Okay, so yeah, because the dependent variable is the one that's dependent on the other one. So down here you have your x-axis is the independent, and then over here you have the dependent, which is the y-axis. Also, we call it response variable, and apparently they're calling it dependent as well. That's a P. Anyway, so they're telling us the dependent variable is nicotine, so that's our response variable. Often I think they actually say response variable, which is even better because that's the terminology we use. The R squared, remember that's our correlation squared, you know, so you could actually take the square root of this if you change it to a decimal, so 0.24. If you take the square root of 0.24, that would give you what the value of R is, in case you were curious, because if you can square it to get it, you know, just make sure you get rid of the percentage first by moving the decimal over to there. Okay, so this is the coefficient determination. So what we're saying is 92.4% of the variation, that's what this is saying down here, 92.4% of the variation in nicotine can be accounted for by the model with TAR. So that's answer B. Another way of saying that is that 92.4% of the variation in the response variable, okay, which is what we're always interested in here, the one on the y-axis, can be removed or accounted for by using the model with the explanatory variable, which is the x-axis, which is the TAR. So that means that there's 7.8% of the variation that's still remaining unaccounted for that's caused by other factors. That's still causing the variation in the nicotine, okay, even after we've used our model and we've removed all the variation by using our explanatory variable, okay. And that's not really that big of a deal. And this 7.8%, that's going to be the amount of variation that we have in the error or in the residuals themselves, okay, which is what we have shown over here. So all this, how it's not fitting the data, that would be the standard deviation, and we square it to get the variation, okay. All right, now what I wanted to show you is on the regression analysis here, they give you variable and coefficient. So the coefficient are going to be the numbers, the variables are going to be telling you, like, is this the slope or the y-intercept, essentially. So the slope is going to be the TAR, okay, so that's going to be our slope. And then the constant, if you think of a constant, that's going to be like the B or the y-intercept. Oh my gosh, it's really hard to read. But if you think about it, the one that's associated with the variable is going to be is TAR. The constant is the one that's not going to have a variable because it's going to stay constant because it's not varying as we vary the TAR. So this is going to be your y-intercept. So when you're writing the equation, our response variable was nicotine. So nicotine with the hat over the top telling us it's a prediction. Okay, prediction. I don't spell. Okay, I do math, so hey, whatever. And then the slope, which is going to be the TAR, that's this number right here, times the TAR. Notice I'm not using y and x, I'm actually using the actual variables themselves, plus the y-intercept, which is our constant right here, okay? So just make sure you know how to interpret this is called a regression analysis, which comes from a computer, by the way. All right, so do you think a linear model is appropriate? So to figure out, I mean, look at the scatter plot, but we also want to make sure we look at the residual plot. So here, you know, you could make an argument that this is curved, If we look at the actual data itself, I mean, does it really look like it's curved? Maybe. We should probably try re-expressing it to see if the r squared would go up. Also, do we have equal spread? Well, kind of. Is this really an outlier? Well, the problem with a residual plot is it's going to zoom in to show you detail. So really, those are not that far off from the line. So it's probably okay. It just depends on how nitpicky you want to get. Okay, so there's more than one correct answer. But you know what you should do? You should look in the back of the book because it's an odd problem and see what the book decides in their judgment. But if I was grading this, I would be pretty lenient as long as you explained your reasoning. Hey, that's it. 25 minutes. I hope you guys either have a good weekend if you're in AP Stats because you're watching this on Friday, or if you're in regular Stats and you're watching this on Monday, I hope you had a wonderful weekend, even though I haven't had it yet because I'm talking to you in the future. I got a DeLorean. I got it up to 88 miles an hour, so now like I travel through time, so it's kind of a big deal. No big deal. Have a good one. Bye.